We're going to move now into graphing constant motion, and this will be the link between the simple formula of speed as distance over time to all the other kinematics formulas. Newton originally derived them with calculus, but over the centuries somebody came up with clever geometric ways of solving these problems because you're not going to have calculus for a couple of years. I want to start off with the importance of measuring time. You take it for granted today that every last bloody thing has a clock. When we talk about measuring things in physics, we need to measure them at a constant interval. So having a good watch was critical to the discovery of a lot of the physical laws. Galileo was stuck using his pulse. This is a watch from 1682, and even today, if I said have this made, it's going to cost you thousands of dollars. But have you ever seen movies of the 1600s? Like, half of people died in childbirth. You got bad teeth and died by age 40. They were making these things by candlelight. This is like crazy level of technology. This is like a crazy level of technology that they achieved by candlelight. Now, why the heck do you need to tell time so accurately? Ships. For ships to navigate, and then eventually for trains and other things. So the search for a super accurate clock had a practical reason. And the man who solved the problem was John Harrison. And there's a movie, here's a link here. You can watch the entire HBO special. It's about 3 hours. It's very fascinating. The actor who played Dumbledore, the second one, plays John Harrison. He spent his life starting by making wooden clocks because he was going to be a carpenter. And he took clocks in his lifetime. He was able to make a clock where the average clock was losing, an hour or so a day. He was able to get his H4 clock to work to 1 second a month, regardless of the weather or the storms on a ship. That is unheard of. In his lifetime, he went from having this clock here, his H1, which was quite a large machine, and it was designed to keep time even when it was on the high seas. His original clock is still functioning, the one made out of wood, 300 some odd years later. And then, in a matter of 20 years' time, he took this refrigerator-sized clock and turned it into a pocket watch. One guy. This watch took an 80-day journey from England to Jamaica, and it only lost 5 seconds of time. That was enough that the ship was within a single mile of its destination. They were lucky if they got the right continent before that. And like any new technology, when these watches first came out, that watch was worth half the value of the bloody ship it was on. But within a few years, these watches came down in price to say from $5 million a watch to the equivalent of like $100,000. They were still expensive, but they became affordable for all ships at seas so they could navigate and not strike things in the middle of the ocean. The British government had a prize for the person who solved the problems for ships being lost due to bad navigation, and Harrison literally cleaned their clocks with his invention, and they refused to ever pay him. This is a time-lapse photograph. Fireflies. Now, if this firefly is blinking at a constant rate, we could actually measure his speed. If we thought he was popping off 1 time per second, we've actually got distance time data on him. These are also time-lapse. Which of these two pictures of fireflies was taken in about 1/10 of a second, and which of these pictures took about 10 minutes to take? Which has got me a bit puzzled. One of these is a long time lapse, one of these is short. But there's something very odd about the picture. And we might stop and discuss this one in class. So let's see how we would get distance time data from something. Let's say we got a stop motion of a person running, and we got them at 1 second intervals, and we decided to extract the distance data from this. So we do this. There he is at 1 second, at 2 seconds, at 3 seconds. And that's what you're going to do on your first activity with this. You're going to read these values off. We have nice 1 second intervals because if we pace our clock quite nicely. Now, how do you read these values? I just know some of you want to say 0.9 meters, don't you? You got a choice to make. It's 0, it's halfway, or it's 1. Anything else than that is fiction. You are allowed to read half of the smallest measurement on your instrument. So you got to say 1 in this case. It's closest to 1. Do not attempt to say 0.9, 0.8. Because if you're going to say 0.8, why not say, I think it's 0.823. So the rules in science are whatever the smallest digit is on your device, you can go halfway in between those two digits. But anything else is considered fictional. This is called precision. So you can give this a try in the assignment. Down here, where I put in 1, you notice I didn't write meters next to it? If your column has already got the correct heading, you don't need to repeat the word meter, 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 meter when it's right there. What if I give you this data? Give you a data set that's already compiled. We had the clock ticking once per second, right? And we collected our data. Distance. Let's graph it. First point, our third point. I can't help it. 4, 5, 6, 7. Hello. 8. Enough. There's our data. Either this person staggered or people weren't measuring character. But this is noisy data. That's okay. How are we going to get the speed? Well, you could do delta D delta T between every single pair of points and go, okay, this was 1 meter per second. Then it traveled 2 meters per second. Then it was negative 1 meter per second. Oh, this is okay. 1 meter in 1 second. 1 meter in 1. So you could calculate every change in speed along here and average it. But that's what that thing does. You put your line of best fit on, you're going to get an average slope, which is a lot nicer than calculating 9 different velocities here and averaging them. So you're going to read the slope off this graph. How are you going to do that? Not this way. There's 2 things wrong with doing it this way. Calculating slope, take the biggest piece of the graph you can. I mean, why not just do some little itty bitty triangle down here? Go big when you're getting the slope. You'll get better results. Easier to read. Secondly, you got all these pretty blue grid lines. Why would you send a slope where you're going to have to go down and try to guess fractions? Pick your triangle so it lands on the axes, like this. See? Now I'm spanning a huge chunk of the graph, and I made sure that I took my slope right at an intersection. So I can just go 8 and 7 and a 7. That's off a little bit. What's going on here? I organized those earlier. But you get the idea? Now you're reading nice even numbers. You don't have to try to guess in between. So, yeah, my units, you drifted. So what's the slope of this graph? Well, the change in distance over here is 7 from 1. It ended at 7. It came from 1. How much time elapsed? The time went to 0. So we have a rise over run of 6 meters in 8 seconds. And that would be the maximum amount of detail I'd want to see. I know a lot of you would rather not write meters here, seconds there. I'm not going to penalize you if the answer is correct, but it is good practice to get into that habit. And typically at your age, you fight the teacher on the units. I did myself. I was like maybe first year university before I was committed to never sending my numbers out naked in the world. If we have a multi-segment graph, it's not a big deal. You just take the slopes where you see them. Take a slope here and you go, hey, this guy was traveling 1 meter a second for the first 4 seconds. Then he sat at 0 speed for 3 seconds. And he really booted at 2.5 meters a second for the last 2 seconds. So I guess this is when Dad said come do the chores. You stopped and then Dad barked and you really stepped on the gas to get home. Okay, easy enough. We've moved on to a displacement time graph, and you should recognize, let's say it was smeared and you couldn't read it here, that this must be displacement, not distance, because it's going backwards. And we're going to look at this and calculate some values off it. So the first one, the distance over time, we go from 7 meters, and we started at 0. So we have 7 meters north minus 0 meters north. And that took place in 2 seconds time. We calculate this out, we get 3.5 meters per second. Highway speed is around 30. So this is a tenth of highway speed, about 10 kilometers an hour. That's a good clip for a person. Then they sat still for 3 seconds. Didn't do anything. And here is where the difficulty hits a lot of students. This segment here. 7 to 3 meters. But the trick is they finished at 3 meters north and they started at 7 meters north. So this is the initial and final here, but for this segment, this is now the initial and this is the final. This is a downhill slope. It's negative. This is the correct setup. 3 meters north is the final position here. 7 meters north was the initial position. Time, the delta time, will always be positive unless this is Star Trek. This thing was going backwards. You get a negative 0.8 meter per second north value. And negative north is south. The temptation on, I would say it's more than half of students, is they see this slope and they go, oh, it's going to be a negative number, and they turn it around and they get 7 minus 3 and they get the inverse. This is a negative slope. I was the same way. You're always like, oh, I hate negative slopes. It's totally common at your age. So don't forget, you can have a negative value. Here, what do we do here? Notice the big change. I've got displacement into the negative values. This is a linear path. Imagine this person, they can only go up and down. There is no left and right motion available because the left and right is time. Okay? Your heart monitor, beep, 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 beep. The data is going up and down only. The sideways path is time. So this person started 4 meters north of this 0 line, say 4 Broadway north, and then they went directly south till they were at the address minus 4 north. They did not travel on a diagonal. That's time. They simply went from 4 north to 4 south, and they did it in 2 seconds. So they went negative in speed. They were going backwards. And when you calculate it, you find that they went from 4 meters south, and they came from 4 meters north. Now, what do you do at this point? 4 meters south is still the same as minus 4 meters north. when we have our vectors, and this will come in big in the second unit on Newton's law, up and down, left, right, east, west, you get to the point where you're ready to add the vectors up, you simply switch the direction so they're all the same. So 5 meters north is the same as -5 meters south. And then you can just drop the vector sign. You just like completely erase this now and just do plain old traditional arithmetic. We get -4 meters per second north. And that makes sense. This person hightailed it from address number 4 all the way to address number -4. An 8-meter journey, and they did it in 2 seconds. So they were traveling 4 meters a second south. What about this segment? Well, in 1, 2, 3 seconds, they traveled 1, 2, 3, 4, 5, 6 meters back to the north. 6 meters back to the north in 3 seconds elapsed time is 2 meters a second. Then this final segment, they traveled south 2 meters in 1, 2, 3, 4, 5 seconds. 2 meters in 5 seconds is 0.4 meters per second south. That's as fancy as we're going to get with displacement time graphs. But the key is that you understand that this is straight line motion in one dimension. This is not a map. It's not a vector map. This is time this way. Here's something else that occurs. Not only do students not want to report negative slopes, but something strange happens. Did this person walking south do anything special when they crossed the center line, the 0 mark on this north-south axis? Did they stop moving here? A lot of my students over the years have said, oh, it stopped moving when it hit the 0 line. I want you to think, did anything special happen at that moment on that blue line? And we can talk about that in discussions. We want to take now a basic concept of slope and area to a much bigger general arena. When I ask you, if you are driving 100 kilometers an hour for 2 hours, how far have you traveled? You immediately notice, say, 100 times 2 equals 200. To make it general, you say, oh, distance is velocity times time, and I can put in any values in the universe into that. You can go from a specific example you can do to writing it down as a procedure, a formula, and you've generalized it. So the concept of area and slope are much more general than you think. To you, slope generally means literally the tilt of a hill or a line on a graph. You can measure it in degrees or rise over run ratio, but it's just a tilt. But I'm going to show you that slope can have much more meaning. I'm going to show you that slope can have much more meaning than that. Similarly, area is something you are used to having units of meters squared. But if the graph isn't displaying length against length, the units of area on that graphing world can be very different from the physical idea, of an area rug. And I'll give you an example. If you plotted the money you made over time, so you go to work one day and look at this, man. Every hour I work, I get another $5, $10, $15, $20, whatever. As you work during the day, the pay you get goes up. Well, what would the slope of that graph be? Rise over run would be dollars per hour. This graph would have a slope equal to your wage rate. What if instead I graph dollars per hour over time and say you are being paid say $20 an hour for the course of a workday, what would the area under this graph be? What is dollars per hour times time? I'll give you an example. Let's say this black line here is at $15 an hour and time is equal to 10 hours. Can you tell me what you got paid? You'll discover that when the graph is showing rate of pay against time, this area here is the money you've made. So the slope of this graph leads you here. The area of this graph takes you back. Slope and area now have a highly specific financial meaning. We're going to do that now with distance time graphs. So here's a displacement time graph. And this is going to be really boring until we move on. This person had a really boring journey. They went out at 3 meters a second, stopped for 3 seconds, and came back at minus 0.8. Really boring. But there are 3 reasons we want to study this. We're going to see that we can see formulas as part of graphing, and this will give us a powerful technique to find the remaining formulas of motion without having calculus and world domination, of course. What if I wanted to graph the velocities here? This is so boring. This thing represents 3 meters a second for 2 seconds. So our speedometer here would just be this line. 3.5 meters per second. I don't know why I did 3.5. Whatever. Yeah, it is 3.5. I got a typo there. That's 7 up, 2 over. That's 3.5. So on a speedometer in our car, 3.5 meters per second would be about here. Right? This is accurate. I made it. It's perfect. So my little speedometer there at 3.5 meters a second would be about 10 kilometers an hour. So this line here would represent the speedometer sitting there for 2 seconds. Then the thing stops. In this interval, the speed came to 0. So the speed graph would just show 0. So the speedometer sits at 0 for 3 seconds. Now the speed goes into the negative. So at this region of the graph, our speedometer would read negative 0.8, which of course regular speedometers are not designed to track, but a GPS would. It would suddenly tell you, hey dude, you're going south. Put the car in forward. So a displacement time graph gives us velocities, and we can plot these velocities on a really boring velocity graph. But it ain't going to stay boring. It's going to get considerably more interesting, but I just need to introduce you to the concept first. Now we're going to see our general capability here. What's the formula for velocity? There it is in all its ugliness with the vector sign on and the deltas. In your head, you can pretend the vector sign is gone and the deltas are off. Speed is distance over time. It's just dressed up a bit. What is the formula for a slope of a line? M is delta y over delta x. Gosh, that looks kind of like the slope of a line formula. Hold on a minute. They are the same. The displacement is the y-axis and the time is the x-axis. If you were in math class, you just would have x here and y here. So this very general purpose formula in math class, when we label these axes with other units, it suddenly has an entirely special meaning. The slope is velocity. Ain't that nifty? Delta y over delta x on a displacement time graph is the very definition of velocity. So the slope of a displacement time graph gives you velocity. The slope of this leads you to that. Can we go backwards? Let's go in reverse. If I have a velocity of 3.5 meters per second for 2 seconds, can I figure out my displacement? Common sense here. You travel at 3.5 meters a second north for 2 seconds. How far have you traveled? Now, what's the formula for displacement? Well, the distance you travel is speed times time. Oh, sure, it's got a delta now. That's fine. That's just in case you didn't start at 0, and delta time in case you didn't have a stopwatch. And you're like, oh, I'm starting counting at 12:31. But this is really just distance, speed times time, just fancied up a little bit. What's the formula for area? Well, in general, area is length times width. What would that be on this graph? What is the length times width of the area under this velocity timeline? Well, length is now speed and width is now time. So, wait a moment, once again. General purpose area, length times width, the area on a velocity time graph becomes distance. So if you could add up the area under this graph, you would get the total displacement. And let's see. This is 1, right? So that's a half. 0.5. 1, 2, 3, 4, 5, 6, 7. It works. Now, do we still count the area under the graph? Absolutely. That's what calculus does. It eventually leads you to calculus, this technique. And you'll learn something else called Riemann sums that leads up to it. A way of dividing up a graph very carefully and calculating the area under it can go a long way to solving our problems. Now I'm going to stop here now and let you digest this. And then we're going to move on into acceleration, and we will be able to prove the remaining 3 formulas you need using geometry instead of calculus. So this is, again, it's a pretty long lesson, but there's no real shortcut around this. And I just wanted to introduce you to this because this leads you inexorably not only to all the math formulas we need in physics, but it leads directly to calculus one day. And you'll go, wait a minute, I see the link. And in university, if you take physics, they will redo all this using the power of calculus.